All right, let's get started with Lesson 10, Gibbs free energy. Now, free energy is going to tie all of our concepts of thermodynamics right here. Gibbs free energy is going to give us better understanding of why entropy is the driving force of a spontaneous process. So, in simple terms, free energy, and we're going to write down the definition here, which is really important. So, free energy, by the way, free energy is a symbol for delta G, all right? G for Gibbs, who came up with the concept of free energy. So, delta G, which is the change in free energy of the system, not, okay? By definition, is going to measure the quality of energy available. All right, quality. So Gibbs free energy measures the quality of energy, how good this energy is. Not all energy is of the same quality. Some energy is junk energy. For instance, heat energy is considered junk energy because heat energy really is not useful to us. All right? What we're looking for is energy that we can create from a system that has good quality. Why? Because it is this energy that Gibbs free energy that we're looking at energy which is free to do useful work. All right, and that's the key, useful work. Good energy, good quality energy can be used for work purposes. And so what we begin to understand is that chemical processes are spontaneous and they increase the entropy of the universe for the purpose of creating quality energy that we can use to do work, to drive reactions that need work or to drive processes that require work to be done. All right? So in other words, what we say is that we use spontaneous reactions and we grab a hold of the energy from a spontaneous reaction that is quality work or quality energy and use it for work to drive non-spontaneous processes at all. And that's kind of how we live as human beings. We eat food in order to get quality energy out of our food to drive in our bodies non-spontaneous processes that just won't occur without that useful quality work. All right? So what we find then is that spontaneous reactions are going to have negative free energy. Oops. Free energy changes. Because they can do useful work. All right, and that is the key. When you get a negative delta G value, when delta G of our system is negative, we'll get a spontaneous reaction that will occur because the increase in entropy of the universe gives us free energy, energy that is quality to be used to do work, useful things. And that is the whole key here. is we need to get that useful energy to do work, to drive processes that are non-spontaneous. Now, delta G can be calculated in a very useful equation that's just written right here. This equation here you need to put to memory. Super important, all right? What it's saying is it ties in really the entropy of the system and the surroundings, all right, and relates it to free energy. So the free energy of a system can be found by taking the change in enthalpy or enthalpy of our system minus the temperature. That's what the T is, temperature. And the temperature, of course, has got to be in units of Kelvin, times the enthalpy or entropy change of the system. Now, I'm going to erase some of this so that I have more room to write here, talking about this equation a little bit more. All right, so this unit right here applies to the change in enthalpy of the surrounding environment. And this right here, oops, I need to erase that. And this term here applies to the change in enthalpy of the system. And so when we add those two together, as we've seen before, plus system, that will give us the entropy change of the universe. All right, so by relating these terms here and subtracting them with the consideration of temperature involved will tell us if this reaction or the process is spontaneous or non-spontaneous, plus is there going to be useful work available. All right, so we're going to use this equation a lot to make predictions about is useful work going to be produced, and is the process then going to be spontaneous or not, as well as that we're going to use this equation to actually calculate the values of delta G. All right. All right, so we have a very important table here that I want you to learn super well, okay? So what we have here is we've basically taken the equation that we just used. In fact, I think it would be appropriate to write that equation right here again. So delta G naught is equal to delta H naught minus T delta S. All right, naught. Okay, so remember that delta H relates to how, let's write this up there, affects the delta S of the surroundings. Okay, and this value is going to affects the enthalpy change of the system. Okay, so keep that in mind. And then, of course, delta G value, and this is going to tell us if these situations lead us to a spontaneous process or not, okay, based on our equation. All right, so here we go, the situation. If delta H is negative, so delta H is negative, that means we have an exothermic reaction. Now, our exothermic reaction is favorable to increasing the entropy of the surrounding environment, and the answer is yes. We know that all exothermic processes are going to create an increase in the entropy of the surrounding environment, so that is very favorable. Delta S of the system is positive. That means the products are becoming more random. That is super favorable. So basically we're saying that the entropy of the system is going up and the entropy of the surroundings goes up. So therefore, delta G will always be negative, and therefore will always be spontaneous. So anytime we have this situation where we have an exothermic process and the system is increasing in entropy, delta G will always be negative and spontaneous. Therefore, we will have free energy available to do work. Now, what if we have a situation where delta H is positive, okay? So that means it's endothermic. Is that favorable? No, because it's going to decrease the entropy of the surrounding environment. And that's not what we want to happen. So that's not a good situation. However, what if delta S is positive? So we have a positive delta H and a positive delta S. Okay? Well, will delta G be positive or negative? Well, that depends on the temperature. If the temperature is high, then the process will be spontaneous and delta G will be negative. So what we're saying here is that if delta H is positive and delta S is positive, the only way for delta G to be negative and therefore our process to be spontaneous is if the temperature is high. Okay, high temperatures only. All right. Now, why is this the case? Why at high temperatures? So you recall that when the temperature is really high in the environment or in the surrounding environment, there's a high degree of random energy. And so the entropy of the surrounding environment is already extremely high. So if we take a little bit of heat energy out of the surrounding environment to drive the endothermic process, just taking a little heat out of a lot of heat isn't really going to change the entropy of the surrounding environment much. So therefore, the only way an endothermic reaction will occur is at high temperatures, never at low temperatures. All right? And that's what this is trying to tell us. All right, what if we have the case where we have delta H is now negative, so we have an exothermic reaction, which is great, it's very favorable. But now delta S is negative, all right, which is not favorable because the products are becoming more ordered. So even though it's exothermic and favorable, the system is becoming more ordered, which is not favorable. So therefore, what's going to be the sign of delta G? Is it going to be positive or negative? Again, it depends on the temperature value in our equation. Okay? It will only be spontaneous at low temperatures. So it's the opposite of the endothermic process. All right? And why is this the case? So recall that when the surrounding environment has a low temperature system or low temperature surrounding environment, the amount of heat energy is really low. So therefore, there's not a lot of randomness or disorder of the energy in the surrounding environment. But exothermic reactions are going to dump a lot of heat energy into the surrounding environment. And when they dump all this heat energy into the surrounding environment, it's going to create a greater amount of increase in entropy. So at low temperatures, there's not a lot of energy in the environment. So exothermic reactions put a lot more energy into the environment. Therefore, the entropy of the environment is going to go way up, and that is going to be in a super favorable condition. Remember that entropy increases in the surrounding environment in an exothermic process at low temperatures always, okay? And that will create a spontaneous process. All right, so what if we have the situation where delta H is positive and delta S is positive, so they're both positive. Well, in this case, it will always be positive. Delta G will always be positive and never spontaneous. This is a non-spontaneous process. If these two situations occur, nothing will ever happen. No matter how much time goes by, this is a non-spontaneous situation, all right? Because essentially it's never going to produce useful free energy, energy that can be used for work. If we don't create the energy for work, the process will never occur, all right? And so that's important. So these are the criteria or situations that will occur that we have to basically think about in order to determine if a reaction will be spontaneous or not, all right, using delta G. There is another way to calculate delta G using what we call delta G of formation values, which we would find in a table, much like we've seen with delta S values and delta H values of formation, where we find those in a table. And we'll use our famous arrangement equation where we take the sum of the delta H or the delta S formation values of the products minus the sum of the delta F formation values of the reactants, okay? And again, these values here we would find in a table, and we just plug and chug into the equation as we've done in previous problems, okay? Overall. So I'm going to summarize really quick what we've learned about delta G and how delta G is used to predict if a process is spontaneous, okay? So summarize all the important points, okay? So first of all, this equation right here needs to be memorized. This equation here is going to help us to determine if a process is spontaneous overall. All right, anytime delta G is negative, the process is going to be spontaneous, okay? Negative delta G's spontaneous all the time, okay? So how do we create these situations, all right? From our table, let me erase this. From our table, if delta H is negative and delta S is positive, delta G will always be negative, okay? This will equal a negative delta G always. This is a spontaneous process every single time, all right? Exothermic reactions are favorable. Increase in disorder of a system is favorable, okay? If delta H is positive, delta S is positive, delta G will only be negative if what? Well, it depends on the temperature, right? So it will only be negative at high temperatures, okay? If we get a situation where delta H is negative and delta S is negative, then delta G will only be negative at low temperatures, okay? And finally, if delta H is positive and delta S is negative, then delta G will always be positive and it will always be non-spontaneous, okay? So these are the 4 criteria situations that you need to know super well for the test. Absolutely need to know them, okay? In class, we will actually practice this a lot more, and we'll also practice using this equation to actually solve for delta G of the system. Now, many times you're going to have problems where you're going to actually have to calculate delta S of the system, where you're going to do so by taking the delta S of the system is equal to the sum of the delta S of the products minus the sum of the delta S values of the reactants. That's common. For delta H, a lot of times you're going to have to use the delta H of reaction is equal to the sum of the delta H of formation values of the products minus the, sum of the delta H of formation values of the reactants, okay? A lot of times you're going to have to use that equation. Solve for delta H, solve for delta S of the system, plug it into this equation with the correct temperature in Kelvin, and you'll get delta G, okay? So we'll go through a lot of these calculations in class, all right? So this is it for now on free energy. Please review this video. Please review your notes. This is such an important concept when it comes to thermodynamics, all right? So that is it for now.